So the question reads, of the numbers 2, 3, and 5, which are eigenvalues of this 3 by 3 matrix? Just some review. Lambda is an eigenvalue of A if and only if the matrix A multiplied by a non-zero vector is equal to the eigenvalue times that same non-zero vector. So when we include the identity matrix and move these terms around, we get this equation here that's equal to 0. Now this equation is true for some non-zero vector if the determinant is 0. And so then the eigenvalues are going to satisfy the characteristic equation when we expand the determinant. So as we've done before in the past, evaluating the determinant for a 3 by 3 matrix is pretty long. We have to get the submatrices, which I've done here. And something I always forget too is the checkerboard pattern of the positive, negative, and positive. So I had to go and review that. So I've expanded everything here, so beautiful, yay. And then we end up with these eigenvalues of 2, 5, and 11. But oh no, so much time has passed because this is a super long way to do this. Yeah, as we know, evaluating 3 by 3 matrices are very tedious, and if you're like me, it's easy to mess up, especially if you're on a time crunch. So we have this other method here. Since we were already given the eigenvalues, we can just plug that into the determinant. Okay, so now we can plug these in really quickly. Okay, I made a mistake. This is 3, and that's 15. Yeah. So now we get 0. All right. Thank you, Rochelle. All right. And then so this is correct. 2 is an eigenvalue because the determinant is 0. Ta-da. All right. Now moving on. Okay, since the determinant is not a 0, it's negative 16, then this eigenvalue of 3 is not correct. Alright. And just to save time, I did the determinant for eigenvalue of 5, and I got a 0, so 5 also works. Yay! So I think the answer for that is C. Whichever the one that says 2 and 5 are the answers, are the eigenvalues. Okay, now this question reads, which of the following statements about the real matrix is false? So, beautiful matrix, 5 by 5, yay. Alright, so the first option here is that A is invertible, which means that if A is multiplied by the inverse of A, we would get the identity matrix. Another way to determine if a matrix is invertible is if its determinant is not 0. So let's take the determinant. Just kidding. If we look at the last option though, which says that the determinant of the matrix is 120, this supports that A is invertible because the determinant is a non-zero number. So if so we can assume that both of these statements are true, and then we can eliminate choices A and E as our answer. Now, so what choice B is saying is that a vector, the eigenvector, can be found in a 5-dimensional space, and the matrix multiplied by that vector equals the vector, then the eigenvector is actually a zero vector. That's a problem because eigenvectors are supposed to be non-zero vectors, which correspond to non-zero eigenvalues. So that's wrong, but let's just double check the other options just to make sure. The C option's pretty simple. Last row of a squared is 0, 0, 0, 0, and 25. You only have 5 here, so yeah, that's right. And then D says A can be transformed into the 5 by 5 identity matrix by a sequence of elementary row operations. If this statement is true, we know that an inverse of A exists because we are able to get the identity matrix by reducing A, which means A is definitely invertible, which means this is true, A is true, E is true, D, and since we already know C is true, that leaves us with B.